Ladies and gentlemen, I'm honored today to introduce you this special session on the energy and the city of the future, which will be a brainstorming of idea about this symposium for the session of 2020. The energy and the city or wheel of the future is a series of international events dealing with the city and the science. The city is a laboratory of meeting between dreams and realities. At a different scale, citizens have to manage daily and to make a better tomorrow. The history of the International Conference on the Energy and the City of the Future started in a simple coffee break in Sergi Pontoise, close to Paris, between Professor Mohamed Dar Sharif from PMI, Professor Nancy from Queen's University in Canada, Professor Ben Nasser from Ines Kashan, and myself, Professor El Ganawi from University of Lorraine. This simple discussion was so rich that we decided quickly about three institutions immediately to create a series of events with a specific spirit to couple under common exchange to mix together scientists, visionists of tomorrow, industrial, and policies of the city. Professor Ben Nasser and Jean-Michel Bricaire helped us continuously and joined the adventure in official sense about the email association in this session of 2020. Thank you for them. Then the symposium became the place to be for dreaming about 2050 city, then starting in Sergi, followed by Queens, followed by north of Morocco in Martil, the scientific basement of the conference being built in French language. Without imagination, future can't find any support to materialize human progress. As sketched on the slide that you see, the city of Longwy, which is a very small city in the north of France, in frontier between Belgium, Luxembourg, Germany, there is an imagination of 2050 and worked 2 days of the EVF symposium on 2017. Without a memory, future doesn't make any sense. This is a picture of our EVF in Fez in Morocco, a city old of 1,200 years. The conference served here as a bridge to connect past and future, history and future. Then we go to the city of Pune in India, close to Mumbai. This city with more than 3.5 million inhabitants become a city who gives some maturity to our event, because the event traveled from the Francophone area to Anglophone area to a big country with a huge question on energy, materials, and cities. Here the edition reached the international dimension with full English presentation and paper published in E3Z proceedings. The next edition was supposed to held in Paris, but as you know, because of the health crisis, our session of today is supposed to make a brainstorming, serving potentially to alimentate the topics for coming events. All editions needed a huge organization. Warm thanks to Professor Desano for dressing the summary of Longwy edition, Professor Zorkani for Faz edition, and special warm to Professor Sridharshan for dressing the summary of Pune edition and for his group for such a huge work for organization, the Symposium of Pune. Our edition conclude with a signed document from scientists, citizens, political leaders on a strong intention on working on a common future of a better city, sustainable, making science and progress in the service of a better life of each and of all. This format making possible the session starting from in Canada at 8 a.m. and ending in India 10 and a half hour later. That allow us a panoramic vision on EVF history and progress for a city taking advantage on renewable resources for housing and mobility, energy, etc. Taking to women in the center of the scientific and the technical progress. Many thanks for Queen University and University Mohammed VI in Morocco for hosting the online edition. Warm thanks to our speaker from Canada, Cameroon, France, India, Russia, and we wish you a big success and a long life to this event serving Homen and the city. Thank you. Welcome.
Just to make sure that thank you very much interesting conference, because this is really a relatively new area for me, because I have been using nanophotonics for other purposes, more on-chip communication, driverless vehicle, those kind of things. So I'm relatively new in this, so this is very enlightening. So I will keep my talk relatively short, because I think we are running a little late. I don't want to keep everyone waiting, so I will keep my talk probably less than 15 minutes. So I will not really talk only about my work. I will talk about the importance of passive heating and cooling, that how we can use solar energy to cool buildings or heat buildings efficiently. And of course, there are many ways of doing it, but metamaterial is a relatively new technology of buildings and cooling. I will give a few examples, because these are a few specific examples to highlight the type of work that has been done and what are the advantages or limitations. And then I will talk very briefly about some of the things that we have been doing recently. Okay. So buildings are responsible for more than 30% of global energy consumption and 90% of global greenhouse emission. So that's only one side of the equation, but also because of the hardware. In Canada, one in five household on average is living in energy poverty. That statistics a few years old. Probably it's even worse now. In UK, it's 1 in 4. So there is really an urgent need to reduce the energy requirement by buildings for heating and cooling. So if we look at the solar spectrum, there is a lot of energy distributed over a wide spectrum. So this area that I'm showing now is a visible light. That's all we need for illumination of building, but the rest of it is really unused. We can, if you can efficiently absorb all of them, then you can efficiently absorb building, heat building. On the other side, in a hot climate, what we really need is get rid of all this extra energy and use only this light for illumination. So by properly engineering the absorption and reflection of solar spectrum, we can go a long way in reduction of energy requirement of buildings. So of course, this is common sense. I mean, this is nothing new that people have been using for thousands of years, different techniques, trombe walls, solarium, roof pond, and so on. Many different techniques for passive heating and cooling. But there are a number of limitations. One thing is a lot of the buildings that we have currently don't have those installed. So retrofitting these things in the existing building will be really difficult. And also, I mean, even if we have this technology already installed in a building, if we can increase the efficiency a few percent, that will go a long way. Because remember, 30% of the global energy is spending only on buildings. So nanophotonic can lead a helping hand in this regard, because there are a number of things has happened in last maybe 1 decade or 1.5 decades. There has been a lot of progress in fabrication. For example, this is a paper I stole from one of Professor Nunzi's paper. This is a solution-based process for growing complex 3D structures. And also we can have very complicated, because the fabrication facility has increased. So we can make very complicated 2D or 3D structures. That's one thing. The second thing is now we have a much better computational resources, high power computing resource and better modeling tool for examining light matter interaction. So we can make things which are more complicated, and now we can also design things and understand how they will work. And that opens up a new area which is metamaterial, where these are artificially structured material which can control the flow of light in ways that was not possible before. So that has been revolutionary in optoelectronics, electromagnetics, microwave, in those domain, but that can also be very useful for controlling heating and cooling of buildings. So I will give you just to be brief, I will give very few examples. One is the radiative cooling. How can we keep a building cool without spending any energy in daylight? So the basic idea is very simple. So the sun is always shining the earth and dumping a lot of energy. And now the earth is hitting maybe around 300 Kelvin, but the universe, the background is really cold, only 2 or 3 degree Kelvin. So the earth is sitting in a very cold background, and it will tend to release the energy. So it absorbs the energy from sun, it heats up, and then it radiates like a black body. So the sun is this red part here, and like a black body, and this is the earth. The earth is radiating around 8 to 13 micron in this region where the earth is re-emitting the heat in the space. And luckily, if you look at the absorption spectrum of atmosphere, this is where is highest. So that so now if we can make a structure that can so the problem is even then in daytime we become hot because we are absorbing a lot of light that is in the visible and near infrared. Then earth is radiating part of it, but a lot of it is still absorbed, so the everything gets hot. But somehow if we can reflect this sunlight without absorbing and then also emit the extra heat, then we can potentially make things even colder than ambient. And that has been done a few years ago in 2014. This in Stanford, what they have done, they have made a multi-layer structure, and this structure is reflecting almost all the visible and near infrared light. Almost all the sunlight is reflected back, and it also emits heat very efficiently. So at the end, what happens, even in daylight, you are getting cooling without spending any energy. So they did a simple experiment and they showed that if you put this multi-layer structure on top of a roof, then you get 5 degrees below ambient. So you are getting air conditioning without even spending any energy. So this is new for us, but this nature has been doing it for billions of years. For example, Sahara ant in the Sahara, they do this, use this structure, exactly the same principle for radiative cooling. That's how they survive in desert. This is a butterfly, same technology. They are using it for billions of years. So we have just started learning it. So now I will give an example of passive heating. So again, I'll skip the slide to keep it brief. So the idea is you will you will let the visible light to go through the window so that you have the illumination, but then you will absorb this light, the near infrared invisible light that you are not really using for anything. So this was an experiment done in 2017, and by using a multi-layer structure where they have nickel and silica, periodic nanoantennas, they were able to increase the temperature of a window by 8 degrees. So that's a lot if you think about a cold day. If you can get 8-degree increase in temperature on the walls and windows without spending any energy, so that's should result in significant improvement in fuel heating efficiency. So what are the limitations of metacells? Obviously, there has to be a few limitations. Otherwise, by this time, it will be used everywhere. So one of the problem is that very often they require periodic structure. For example, the structure that I'm showing here. These are really complicated structures. So they are using electron beam lithography or focused ion beam or some technology that is really suitable for small scale demonstration, but you cannot really make things which are square meters maybe. So this will become prohibitively expensive. And the second problem is that most of the time when people are publishing these papers, they are trying to get good result and not really thinking about practicality. So they are using noble metals, gold or silver. So the cost will also be prohibitive. So large scale adoption will really need to change this scenario. So here I will give a very simple example of the kind of thing we are doing without going into details for the interest of time. What we are trying to do is develop a window which will have two coating. One side will be for heating and the other side will be for cooling. So the idea is that if you can put this thin layer of coating on the as thin film on top of the window, in in winter, what it will do, it will absorb most of the infrared light, let the visible light to go in the room, so you will get heating. In winter, you will reverse the structure. So now you will have the radiative cooling. So by using the same structure and without spending any energy, you should get both heating and cooling. So this is still a work in progress. We have done the design for heater, but we are now working on the cooling system. So these are summary of the result for two of our design that we have done, and this will be submitted for publication next week. So we have a multi-layer structure made of silica and titanium nitride. So those are easy to grow material. Titanium nitride is very widely used for coating material. There are already industrial systems that can coat window with titanium nitride, and silica or material like silica is also easy to grow. So what you see here that the mean transmittance in the visible region is 68%. So you're not really losing much of illumination. And overall, 42% of light of the all solar spectrum is absorbed. So there is another alternate design here, which is very similar but have one additional layer. The heat absorption here is more than 54%. So we also wanted to estimate that how much, what will be the thermal performance. So what we found that if you are under direct sunlight, AM 1.5, then you have a 21-degree increase of temperature of the window for the first design, and for the second design it's 27 degree. So under direct sunlight you can have more than 20-degree increase of temperature of the window, because a lot of the light is being absorbed by the window. And unfortunately we have not been able to do the experiment yet because of the COVID. I mean, the access in lab is very limited, but we have simulated all the papers that we can find, and we have been able to reproduce the temperature increase for all of them. So we are quite confident about the validity of these results, but we want to get the experiment done as soon as possible, as soon as they will allow us to go into the lab. So another thing is that the angle will also be a critical thing for the window, because I mean you will not get direct sunlight at 90-degree incidence. You can have diffuse light is coming for all angles. So a common problem with the periodic structure people has done is very angle dependent, but this structure is almost angle insensitive. So for example, here we are showing the transmittance, reflectance and absorbance for 0-degree and 30-degree incidence. You can see there is not really much of a difference. I'm not really going into the details of all these plots because I know that a lot of the speakers are still remaining eager to give their talk, so I'm trying to be very brief, and we can discuss later if anyone is interested. So this design is also very versatile. So the first design I showed, and a growing thin layer of nickel is not really too challenging. There are a lot of result in the literature where people has grown very thin layer of nickel, and it's really chemically stable. So our performance is almost same as titanium. I think metamaterials are promising both existing and new buildings. Of course, this is not meant to be replacing all the other technology, but it can be really helpful because these structures are relatively easy to build. These are just thin coating on existing windows or wall or whatever. Just thin coating of multi-layer structures, multi-layers of easily available materials. So cost reduction and mass fabrication still remain key challenges, but there has been a lot of progress, and the work I presented is only one example. There are lots of good work going on. And in addition to the complicated structure people are doing, even simple multi-layer planar structure, if done carefully, can go a long way for passive heating and cooling of buildings. Thank you.